Hello everyone, Mr. Bowman here. I hope your second semester is going well so far, and I hope that you are understanding sequences and series. Today, in this video, we're going to talk about the idea of writing a series, which is the sum of the terms in a sequence, using sigma notation. There are slight differences here if you are in anyone else's class between the notes, but I will point those out as we go along. So let's get started. So the first thing I want to point out is this sigma part right here. So I'm going to circle this. This is the Greek letter sigma, and that's why we call it sigma notation or summation notation. So that means sum all of the terms that follow. The part next to it that I am circling in green is the explicit rule. Remember, we talked about the idea of an explicit rule versus a recursive rule. That will be the explicit rule. K is called the index, and K equal 1 is the first term. So index and slash first term, and I will point that out by way of examples. And then finally, n is the last term in the sequence, or the last term number. So let's take a look at a few examples and write out the series. In other words, convert from sigma notation to just plain written out notation. So in this first example, we are taking the explicit rule 3 times the value of k, and we are starting with the first term and ending with the fifth term, and we are adding them all up. I do want to point out that if you are using the Pearson homework, you are likely going to have to put parentheses around the entire explicit rule, because that way the program will know exactly what part is the explicit rule and what part is not. So, for example, in number 1, our first term would be 3 times 1, which is 3. Sigma means plus, so we put a plus there. Then we would increase the index number by 1, so 3 times 2 would be 6, plus 3 times 3 would be 9, plus 3 times 4 would be 12, plus 3 times 5 would be 15. So that would be our expression for that summation. In number 2, you will notice that we start with the fifth term and end with the eighth term. Now, in this case, we don't need to put parentheses around the k squared because there's only one part to that expression compared to the 3 times k. But it's not a bad idea to do that anyway. So the first term in our sequence is going to be 5 squared. Sorry, I said sequence. The first term in our series is going to be 5 squared plus 6 squared plus 7 squared plus 8 squared, or 25 plus 36 plus 49 plus 64. For those of you not in my class, this next example is not in your notes. You might want to take a minute and write it in. And the reason I picked this example is for the reason that we use a different letter for the index. We use n instead of k. It's also a trig function, which you might find somewhat surprising. And we start the index at 0. Those are all things that you might see from time to time when you're using sigma notation. So the cosine, the first term in our series, is going to be the cosine of 0 times pi plus the cosine of 1 times pi plus the cosine of 2 times pi plus dot 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 all the way out to the cosine of 6 times pi. And if we were to go back and evaluate that, we would say, okay, well, the cosine of 0 is 1. The cosine of 1 is -1. The cosine of 2 pi is 1. The cosine of all the rest of them, all the way up to the cosine of 6 pi, which is 1. So that is our series for that example. The next thing that we're going to do is we're going to take the series given to us in the forms shown below, and we're going to first write an explicit rule. We're going to use k instead of n just to be consistent with our textbook, and then we're going to write that series using sigma or summation notation. Now you will notice that in your notes the numbering is slightly different if you're not in my class, but they are the same examples. So the first thing we want to do is we want to take a look at these series and write their explicit rules. So what you will notice with the first example is that the first value, which we are going to call A1 or term 1, is 2, and then there's A2 and A3 all the way up to A4. So we have a rule that's going to be A sub k is equal to, well, you should recognize this as an arithmetic series because there's a constant difference. We keep adding 6 each time, and so our first or initial value would be 2 plus the common difference, 6 times k minus 1. While I like the explicit rule in its current form because it clearly shows you the initial value, the common difference, and the fact that you're going to add the common difference k minus 1 times, when you write this series in summation notation, you're going to want to simplify that first. So if we were to distribute the 6 and combine like terms, we would have the following, 6k minus 4. And so our sigma notation or summation notation would go like this. It would be the summation from k equal 1, because that's our first term, up to 4, because that's our last term. And then in parentheses, we would write our explicit rule, 6k minus 4. And this would be an example where you do want to put this in parentheses, because if you don't, Pearson website is not going to know if you are summing the term 6k or the terms 6k minus 4. I want to take this first example and rework it if our index started at 0. So instead of calling the first term A1, what if we called the first term A0? Then the second term would be A1, and the third term would be A2, and the fourth term would be A3. If we were to do it that way, we would write our explicit rule slightly differently. Again, we would start with the initial value, and we would add the common difference, but we would add the common difference k times instead of k minus 1 times. Now, obviously, the explicit rule looks slightly different, and I will show you in a moment that we get the same result. So if we use that explicit rule, our sigma notation would be slightly different. It would be from k equals 0 to k equal 3, and we would have 2 plus 6k or 6k plus 2. And we can verify that this works out correctly by simply plugging back in the index values. So if we were to plug in the index value of 0, we would have 2 plus 6 times 0. If we were to plug in the index value of 1, we would have 2 plus 6, which would be 8. If we were to plug in the index value of 2, we would have 2 plus 12, which would be 14. And finally, if we were to plug in the index value of 3, we would have 2 plus 18, which would be 20. And you can verify that that is the same as the series that we started with. The reason that I point this out is because occasionally when you are looking at sigma notation, sometimes you will see it written as it is here in red, starting with k equal 1, and sometimes you'll see it written as it is in green, starting with k equals 0. The explicit rules are going to be written slightly different in those cases, so you just have to pay attention to that. In the next example, we are going to write the explicit rule. We're going to stick with the starting with the index value of 1. So our first term, we'll call it A1, is right there. And if we just count out A2, A3, A4, A5, so we're going all the way up to A5, we need to write our explicit rule. So A sub k is equal to, the pattern here is that we are adding 4. So we have a constant difference of 4. So we start with our initial value of -3 plus, well, actually, plus a negative or minus 4 k minus 1 times. And we're going to simplify that. So we have -4k plus 1. And when we write this using sigma notation, we're going to have the summation from k equal 1 to 5 of -4k plus 1. Why don't you pause the video here, use this example, and try writing it using an index starting at 0 and going to 4. All right, so if you did that by starting with an index value of 0 and ending at an index value of 4, your explicit rule is going to be -3 minus 4k, and your summation notation is going to be k equals 0 to 4, and the expression, the explicit rule, is going to be -3 minus 4k. Next thing we're going to do is we're going to move on to number 3, and number 3, if you take a look, is a geometric series. So we're going to again write the 120 as our first term. Simply count off 2, 3, 4, 5. So the 7.5 is our fifth term. We need to write the explicit rule for this. So our explicit rule is A sub k is equal to the first term, 120, times the common ratio. The common ratio is -1/2 to the k minus 1 power. And that's as simplified as we're going to make that. So to write that using sigma notation, we're going to write from k equal 0, from k equal 1 to 5. And we're simply going to put the explicit rule in there. So our explicit rule is 120 times -1/2 to the k minus 1 power. If you were to write the explicit rule for number 3, starting with an index of 0 and going to an index of 4, your explicit rule in green, I'll write right here, would be A sub k is equal to 120 times -1/2 to the k power. And then your summation notation would be using that explicit rule. The only difference would be that you start with an index of 0 and end at an index of 4. So it would look like this. The summation from k equals 0 to 4 of 120 times -1/2 to the k power. In example number 4, our first term, we'll call it A1, is 2,187, and we see that we have 3 terms in that. Now this might take you a little while to figure out, but the series that we have here is a geometric series, and the common ratio is 1/3, so our explicit rule is A sub k is equal to the first term, 2187, times the common ratio to the k minus 1 power. And our summation notation for that is going to be from k equal 1 to 3 of our explicit rule. So 2,187 to the 1/3 times 1/3 to the k minus 1 power. And again, if you want to rewrite that, starting with an index of 0, it's going to be basically the same rule, except you're going to have a sub k is equal to 2,187 to the 1/3 power times 1/3 to the k power. And you would use that in your summation notation and start your index at 0 instead of at 1. The last two examples that we're going to do are pretty straightforward. Our first term is a sub 1, or we're going to start with the first term. We're going to call it a sub 1. And so in number 5, our explicit rule, a sub k is equal to the first term, -1. And you'll see the pattern here is that we keep multiplying by -1. So times -1 to the k minus 1. And the difference here is that you see this dot, dot, dot at the end. So basically we have an infinite number of terms. The difference in our notation is pretty straightforward. We're going to say from k equal 1 to infinity instead of a finite number. And we're going to put our explicit rule in there, -1 times -1 to the k minus 1 power. And then our last one is neither an arithmetic or geometric series. Our first term, a1, is 1. And if we try to count out the terms, we don't really know how many terms there are. So this gets a little bit tricky, and we need to think carefully about this. The explicit rule is basically we're going to take our index value, add 1 to it, and cube it. So I'm trying to figure out what term number this is, and if I simply call that the nth term, well, that seems to work because then I could make my upper limit on my summation notation n. But if I work backward and I go to my initial term, a1, well, let's plug 1 in. 1 plus 1 cubed is 8. So really, if I do that, a1 would be that term. So that kind of forces me to use a sub 0 to make this easier. So our explicit rule, a sub k, is equal to k plus 1 to the 3rd power. Okay, you'll notice I switched to k here, and I'm going to show you why in just a minute. So we're going to write our summation notation. We're going to start at k equals 0. And I need to tell the reader when to stop adding terms. Well, I'm going up to the nth term, so I'm going to put an n up there at the top, and that's why I switched my index to k, so people know that we're using k, the index value that changes, but we're stopping at the nth term. So our explicit rule, k plus 1 cubed. And that, ladies and gentlemen, is sigma notation. We are going to end this lesson with a slightly different activity, and this is the question. What is the sum of the first 100 integers? So 1 plus 2 plus 3 plus all the way up to including 100. Pause the video, take a moment, see if you can figure out a relatively easy way to do this. So there are variations of the story behind this, but basically it goes like this. A mathematician, his name was Carl Friedrich Gauss, was in elementary school in the 1700s. And one of the stories says that his teacher got annoyed with him and told him to go out in the hall and sum these integers from 1 to 100. And at that time, they didn't have calculators or smartphones or photomath. So Gauss goes out in the hall, walks back in a few minutes later, and he's got an answer, to the amazement of his teacher. And what he did was the following. Gauss recognized that if you were to take the first and the last term, they add up to 101. If you were to take the second and the second to last term, they also add up to 101. If you were to continue doing that, the pairs would add up to 101. And eventually, what you got was you got 50 pairs with a sum of 101. So you could say, oh, 50 times 101 is the sum, we'll write it like this, summation of k equal 1 to 100 of a sub k, and our explicit rule in this case would be k equal 1 to 100 of k. It's that simple. That's it for this lesson. Have a good day, everybody. We will talk more about this idea of summing, or quick ways to find the sum of an arithmetic and geometric series, in the next class.